welcome back to the second part of the training and validation video. So in the last video we trained 3 versions of the model by changing the camera resolution across the 3 different versions. So just to show again, the smaller resolution 320 by 180, and we can click the charts to kind of see how it worked out. And these are the metrics during training. So there is still the split between the training metrics and the test metrics, which are against the validation data set. But this is the floating point model that's being trained. So now what we'll do is go run validation. We'll compare the floating point model to the quantized model to see the change in accuracy as we quantize to 8 bits for inference on the edge device. And we'll also compare the 3 models against each other to see how they do. We'll first do the validation entirely within the DeepView Enterprise UI, where the models, including the 8-bit quantized models, are running on a cloud instance for validation. But then we'll show how to download the data set onto a Raven device and perform the validation directly on device, which will also give us timing information and just confirming that the results do in fact match. So we'll switch away from the training UI now. Again, we click the menu in the top right where all the different views are available, and we'll pick the validator view. Now this works largely like the training view in that we create, sorry, I got an overlay here. There we go. So when running on the Maven, you'll see later this user managed validator, but for now we want the cloud managed or fully managed. So we'll select camera size testing. We'll start with our 320 by 180. We can select the models. So let's start with the original Keras models. So these are our floating point models that we trained. We'll validate on the Raven indoor dataset and the default annotations. This allows us to, as we saw earlier, we have a train val split. So 80% of the data set is for training, 20% is held out for this validation. But we can also create completely unique data sets for testing, which don't even have a subset, like a split subset in the training, but we're showing this today. Detection threshold. We can look at precision recall graphs to kind of pick an ideal threshold. We'll keep the 0.5 default right now, and that's when we decide that an output from the model has a high enough threshold to be considered a valid detection. The detection window size within the occupancy grid, a window size of 1 means that the prediction needs to be exactly on the cell matching the ground truth, whereas the window size of 3 means that any neighboring 1 cell can also be considered valid, and they're separated so we can see the metrics with a window size of 1 as well as 3. 5 is another option. Now for this data set in ultra short range mode, being 2 cells off, we would consider that too much of an error, so it's not really valid here. But in certain cases where maybe you're detecting out to 42 meters and 2 meters is okay of an error, you might select the window size of 5. So with that, we click Start Session. We of course need to give it a name first. I missed that part. So camera dash 320 by 180. We'll just give it the same name as the training session. And then I'll go ahead and just quickly create for the yellow experiments that we ran. And keeping everything else as default. And finally, the last one. 640 by 360. And there we go, and that's all that's needed. Now while this is running, I'll also go ahead and repeat the same, this time with the quantized model, so we can compare those. Again, all these validation sessions can run in parallel. So we'll run all those, and then to run on the device, we'll need to go do that manually. So camera 320 by 180. Call this date, quant. And then just one more. After I start this last one, we'll go ahead and speed up the video and skip to the end once the validation is completed, and we'll go over the results. 20 by 360. Okay, now all 6 are running, and we'll be back in a moment. Okay, so all the validation sessions have now completed, so we'll start looking at them. We'll take a look at the 320 by 180 Crass model to begin. It's this one over here. So we'll open this up. So the charts for Validator give us a little bit more insights into the data set and how the model performs. So briefly, we have the metrics of precision, recall, F1 score, and IOU between the 1x1 and 3x3 kernels. We have precision recall chart. We have another precision recall at various thresholds. So the same data, just a sort of a different way to see it. We can quickly see where precision and recall intersect. So in this case, it's almost exactly at 0.5%, or at 0.5 at 50%. But you'll see sometimes, it could be a little bit higher or lower. So it helps make decisions about where you would want to set the threshold of the running model. The following charts are heat maps of how the data set is performing. So first is on the ground truth, is just showing us the distribution of annotations of the occupancy grid across the whole data set. So we can see there's definitely, a bias to up close in the middle here. Now this is a, square 8 meters to the right, to the left, and in range. So parts of this are not actually in the field of view anyways, but you can see this data set could certainly be improved lateral and in terms of distance. Now this is a small indoor data set, only 20,000 samples, and we'll see in extended videos of building a larger outdoor optimized data set how the distribution is wider. Then we have this heat map showing true positives. So this is where the model is correctly predicting detections. So, here 72% of the people in this cell are correctly identified. Then we see our false positives, and we can can see, most of the false positives are around the edge of the field of view. And then our false negatives, similarly, are mostly concentrated around the edges. Inference timing, in this case, not super informative since this is run on a cloud instance. We'll see the timing when we run on the embedded device and give more meaningful results. In fact, give weirdly better results than these times. I'm not sure what was happening here, but these times are obviously pretty high. But that gives us the crass accuracy. So if we look at, say, our F1 score, so 77.62%. If we go look then at the quantized model, which unfortunately the screen recording overlay is blocking my exit button. Escape? Nope. Okay, we'll have to go the long way around. Okay. So the quantized version of this model is over here. Again, just looking at the F1, still 77%. So we see maintaining a good level of accuracy. So now what we'll do is actually compare the two, which is an easier way to see the differences than trying to remember, as I clearly forgot. So I've selected 320 by 180, the Keras model, and 320 by 180, the TF Lite model. If we now select compare sessions, we get a nice side-by-side view of all the charts and get to compare how the model performs. We see the timing of the quantized model are better, though still a bit surprising, because I can tell you these numbers are quite lower on the embedded target, so we'll have to go see why we're seeing that on the instance. But it's probably running, I guess, on, well, it's not running on a CUDA optimized instance for one, so that'll cause some slowdown. This is running on CPU, not a super powerful cloud instance, and when we're running on the Raven, we're of course running the model on the NPU accelerator. But let's focus on these high-level accuracy metrics. So again, the float model, we were seeing F1 score 77.62, and for the quantized model 77.44. So just a very small drop in accuracy in this case between the float and the quantized model. And I could say, after looking at many of these charts, that's typically what we get from the fusion model, is sub 1% drop in accuracy when we quantize, and that's what we want to see. These charts, and then we'll do a different comparison. We'll go back to validator, and this time we'll select just all the quantized models, so the first three, and what we'll do is compare the accuracy of the change in camera resolution. So I've selected these three, I'll select compare, and now we get the three charts. So from largest to smallest input resolution, and we see F1 score, it's a good metric. We go from 77, roughly in half, to 78, to 79, and a little bit. So the accuracy does improve as the model goes up, but still it's pretty close. And this is, again, ultra short range mode, 8 meters. The camera resolution, it's not going to make a big impact at this range. But as we look at further ranges, such as the medium range that we were recording in previous videos driving outside, when somebody is 20, 30 meters away, the higher resolution becomes more important to be able to make them out. So that's the overview of the validator from the cloud side of things. In the next video, we'll go and show how to load the dataset or the dataset cache onto a Raven platform and perform user-managed validation. So we'll have all these same metrics, which we expect the results to match from much testing. We see that the numbers hold when transferred to the embedded device, but these timing metrics at the bottom will change a fair bit, because they'll now be running on the NPU accelerator on the device, and we certainly don't want to be seeing these types of outliers. So that'll be the next video. Thank you.